As you heard this morning, nitriding is one of the pioneering surface engineering processes. However, despite it's quite an old process, several modifications to the original process have been conducted during the years, and nowadays it's a full technology which is capable to solve modern problems as well as the old ones. This furnace over here is capable of a number of surface modification techniques, some of which are pre-oxidation, which is an aggressive chemical attack on the surface intended to increase the surface area of the material. I will explain further why is that. We can also passivate the surface to render the surface more inert to atmospheric corrosion and thereby extending the component life. Gas nitriding, which is a thermochemical process. Plasma nitriding, which is a physical process which at the end obtains the same effect as the gas nitriding but in a cleaner way. And both gas and plasma carbonitriding of the components. Now, nitriding is the introduction of nitrogen in the surface in order to form nitrides on the surface layer and pinning the dislocations of the surface, making the surface harder and more wear resistant. Now, if we have a look at the furnace, at the various components, we can see that the basic components of all heat treatment furnaces are present. There's the vacuum system, which is the Roots pump, the mechanical pump, and the gas flow control valves connected to the furnace. The chamber, in this case, is slightly different from the ones we've seen before, because this chamber over here is a hot wall chamber. In other words, the outer shell of the chamber is cooled by air, while the inner shell of the chamber, if we open the chamber, this is the inner wall of the chamber, or as is termed by the technical jargon, is the inner bell. This part of this chamber is allowed to heat up to the process temperature, while in the space in between there is cold air which is forced by the upper ventilator. This configuration allows a more flexible control on the temperature inside the furnace, not just by controlling the heat input or the energy input by the resistors, but also by cooling the furnace, thereby reducing the operating window or the control window of the temperature. When the furnace is operated in plasma mode, there is a third temperature control, and this is achieved by positioning the thermocouples inside the chamber close to a big and a small component, thereby thereby controlling the different thermal capacity of the components inside and regulating the plasma power, which is an additional heat input inside the furnace. In this case, the target temperature is set 10 degrees below the operating temperature, and the excess 10 degrees is achieved by increasing the plasma power. So, if we have a look inside the furnace, we see that there is the table which supports the workload, and the table is mounted on 4 isolating mounts. Inside these metal cups, there are a ceramic cap which electrically isolates the table from the wall of the furnace. This is necessary for plasma nitriding, where the work inside the furnace is set to a higher potential in order to accelerate ions towards the components. Now, if we have a look at the exterior of the furnace, we see that there are various components attached to this furnace in order to make this furnace more flexible. There's the gas rack, which is used for gas nitriding. This flow rate controls or monitors the nitrogen flow rate inside the furnace. This one monitors the ammonia flow rate inside the furnace, air, and CO2. CO2 is used to produce carbonitriding coatings or surface modifications. At the back of the furnace, there is the heat exchanger, which cools the nitrogen during the cooling process. While at the top, there's the burner, which burns out the hydrogen and ammonia residues, which are exhausted into the atmosphere. So they are rendered harmless before entering the atmosphere. Now, let me explain the procedures by which the nitriding process takes place. The first step in all cases is cleaning. Cleaning is a very important step in all surface modification technologies. Despite nitriding is a somewhat rougher technique, within inverted commas, it still requires a high degree of cleaning. And this is achieved by washing the components with a solvent, not water, in order to remove all oxides and or loose oxides and greases on the surface without corroding the surface of the components. The components are afterwards inspected and mounted into the furnace. The mounting, the positioning of the components inside the furnace is very important. Adequate space must be allowed for gas circulations around the component in order to modify the whole surface of the components. Now, some components are adaptable for gas nitriding, others are adaptable to plasma nitriding. In the case of plasma nitriding, the restrictions are very stringent. The problem lies in the fact that if there are tiny cavities inside the component, electrons lying in between these cavities get reflected to and from the negative charged sides of the component. This oscillation of electrons generates high intensity plasma, which is known as hollow cathode. The temperature in these regions can increase very rapidly and reaches very high values, whereby melting the component. So in this case, there are two alternatives. Either the cavities are blanked before the process is initiated, or gas nitriding is conducted instead of plasma nitriding. Gas nitriding does not affect these surfaces in any case, because in this case we just heat the components in the presence of ammonia, which dissociates and thereby liberating nascent nitrogen. Nascent nitrogen is important for nitriding because single nitrogen atoms are small enough to penetrate inside the components or in the surface layers of the components. Now, if we have a look at these two components over here, we can see the two extreme cases. This is a very plain and simple phase, which is very amenable to plasma nitriding. There are no cavities except from these three holes, which can be easily blanked using the bolts underneath. In the other case, we have a small component whose important surfaces are a series of cavities. In this case, blanking the holes would render nitriding useless because these are the surfaces which we want to protect. So this type of component is suitable for gas nitriding, and plasma nitriding should be avoided. The next step is evacuating the chamber. Now, both in gas and plasma nitriding, there is considerable amount of hydrogen present inside the furnace. So it is crucial that all oxygen is removed before the furnace is heated. Otherwise, an explosive mixture is generated inside the furnace. So the first step is to evacuate the air from the furnace and rinse the vacuum generated with nitrogen. The nitrogen is afterwards pumped out so that all the atmosphere, original atmosphere inside the furnace is removed. The next step is heating the components to the required temperature. Now, nitriding is usually conducted in the temperature range between 450 to 570 degrees C. Now, heating components in this range, which is considered to be low temperature in surface engineering terminology, is a very slow process in vacuum because the radiation at those low temperature is very, the energy conducted by radiation is very limited. So in order to heat the components rapidly, the pressure inside the chamber is increased in order to achieve convection. So we have convection, transfer of heat from the walls of the furnace to the components, and we have also radiation. Once the temperature inside the furnace reaches the target set point, we move on to the next step. Now, the various steps are controlled by a very advanced PLC, so the whole process is completely automated. The PLC is equipped with a graphical user interface with a mimic of the process showing all operative parameters and the various components which are put into service. The PLC also acquires the data, the process data, and stores it in its non-volatile memory, which can afterwards be retrieved in the form of a hard copy for eventual litigations or for any necessity. Once the program has been selected or once the program has been inputted into the system will follow step by step the required procedure and will start to introduce the various process gases. Now, in the case of gas nitriding, once the temperature has been reached, the system will introduce ammonia. The usual procedure is to introduce a relatively high dose of ammonia and operate at a temperature around 520 degrees for a few number of hours to create a high gradient of nitrogen into the outer surface. The temperature is afterwards increased, keeping the concentration of ammonia constant, allowing for nitrogen to diffuse inside the material, creating a diffusion zone which supports the high wear-resistant surface of the component. It is important to create a deep diffusion zone because it is useless to have a very high hard surface without a tough and supportive layer underneath. Otherwise, the surface will crack and chip off. In the case of plasma nitriding, a tiny amount of nitrogen is introduced through a series of leak valves and hydrogen to achieve the required pressure. The pressure is monitored by controlling the flow rate of the gases and by using a metering valve which throttles the input of the vacuum pump, thereby controlling the pressure inside the furnace. It is important to keep the pressure constant because the pressure controls both the ion energy and the plasma power. The next step is to cool down the components. Once the components have achieved the required depth and the required amount of white layer on the surface, these must be cooled rapidly to stop the diffusion process. If the nitrogen supply is interrupted and the components are allowed to cool slowly, nitrogen from the surface will keep on diffusing and thereby the surface hardness will decrease. So a large amount of nitrogen is introduced rapidly inside the furnace and circulated through a heat exchanger. This will cool the furnace rapidly and stop the diffusion process. Once the furnace has reached a temperature of 60 degrees, plus or minus few degrees, the components are ready to be examined and tested for the normal QC procedures and returned to the customer. Any questions?
Hydrogen will not interfere with the...
Hydrogen is a catalyst for the nitriding process, and it has two main functions. In the case of plasma nitriding, hydrogen achieves the required pressure without interfering with the heavy ions moving inside the furnace. In the case of the gas nitriding process, it combines with any oxygen present in the gas, which is at a higher pressure, and keeps the atmosphere inside inert. This machine over here is TechVax 221 ion implanter. The main components of the machine are the vacuum chamber, the control panel, which is remarkably similar to the one you've seen at the other side, a high voltage power supply, which also incorporates a number of power supplies, which operates the various components, or rather which supply the various components, the gas cylinders, and if you move over here, the vacuum system of the machine. We have a diffusion pump, a large diffusion pump, and a mechanical pump. Now, the size of the pumps compared to the volume of the chamber are rather large. This is necessary as Rod already said this morning in his excellent lecture, in order for the ions to travel a large distance inside the chamber without getting scattered, they need a very high vacuum. Now, this machine over here can operate at a vacuum of between 2 to 6 times 10 to the minus 8 millibars, despite the high gas flow rates. And this is achieved by a comparatively large pumping speed of the vacuum system. Now, mounted on this chamber, we have the primary ion source, which operates at around 100,000 volts and can deliver a maximum current of 3 milliamps. And the secondary ion source, which is a microwave ion source, NECR ion source, electron cyclotron ion source, where we have a microwave source and a quadrupole magnetic field which oscillates electrons to generate a high intensity plasma. At the far end of the chamber, we have a rotary water-cooled table which manipulates the components in such a way as to expose all the facets of the components to the ion beam. This technology has a big disadvantage in which the ion beam travels in a straight line. And in order to hit or to treat the component from various sides, we have to manipulate the component continuously. At the bottom of the chamber, we have an electron gun evaporation source, which can evaporate a wide range of condensable material. And on this side, we have a number of gas cylinders which supply various gases. By combining various gases with various condensable material, it is possible to deposit any required coating. A big advantage of this system, or rather some big advantages of this system, are that the range of material which can be created or deposited in this system is very, very wide, much wider than the other equipment which you've seen. And the biggest advantage is that all processes take place at room temperature. Now, having an operating range between 20 and 60 degrees C makes this machine suitable for almost all engineering materials, and the fact that all components of the coatings are controlled electrically introduces a high degree of control on the process. Also, because the chamber operates at room temperature, it is possible to incorporate a wide range of sensors and optical devices which can monitor the coating process in real time. At the top of the control panel, we have various additional components. The first one, which I'm indicating here, is an oscillating crystal or a microbalance which monitors the deposition rate continuously. It can monitor the rate at which the coating is thickening, and it is so accurate that it can detect one atomic layer at a time. The other components, these are the vacuum control systems, a high voltage power supply for an eventual substrate biasing, and mechanical manipulation of the components inside the furnace.